Hello everyone. So I'm Pratap from MIDAS and Development India, working as a senior structural engineer for India, Middle East and Africa region. Thank you for attending the today's session on integration of MIDAS Civil with Grasshopper and Python. So if you have any questions while the session, so feel free to ask in the chat box, or we can answer them at the end of the session as well. Okay. So let's start. So basically, the integration of visual scripting tools like Grasshopper or even the coding languages such as the Python, so etc. They are actually very important thing in the structural design, and this basically actually it's a like herald a new era nowadays. So it allows not only modeling the complex shapes but also enables the reuse of the design data for repetition of the projects, and also for the generation of the drawings, generation of the reports, and also it facilitates the flexible adoption for the model changes as well. So you don't need to start with a new model, or to modify each and the same model with the various options available in that particular tool. So it's better to use the integration with the other tools as well. So that we will discuss in this particular session. Moving on with the contents of this today's session. So we'll first talk about the Python. So what exactly the Python and how it will works for when we are talking about the civil engineering structures. Then setting up the Python environment when we will deal with the link with the MIDAS Civil Linux, and we'll take up one example that is the simply supported BIM, how the Python script, or we can say Python code, can be created with reference to the JSON manual, which is available for the media between the MIDAS Civil Linux and the Python. Further, we'll also discover about the Grasshopper. So it's a newly created actually the interface, or we can say the integration, and so we generally call it the MIDAS GH. There's a MIDAS Grasshopper link, and how we can utilize this particular Grasshopper for the parametric modeling of the any type of structure using the Civil Linux integration. So setting up the Grasshopper environment and following with the example and in summary. So Python is a high level general purpose programming language, and its design philosophy emphasizes the code readability with the use of significant indentation. The most common cases are we can use this particular integration with the Python with the optimization, that is a section optimization, load combinations, and batch file creation. Okay. So there are actually the various applications available. So the Python integration can be used on a server to create the web applications. So it's a general application of the Python. It's not just related to the MIDAS Civil only. So first was regarding the used on a server to create the web applications. It can be used to along with the software to create the workflows. So as I said, this is the application which you are going to use for the today's session. Then the Python can connect to the database systems, and it can also read and modify the files. The Python can be used to handle the big data and perform the complex mathematics. It can be used for the rapid prototyping or for developing the production ready software. So even through the Python, we can create our own execution files which can be run and can be extracted and linked with the our in-house softwares as well. Okay. The major key features and purposes are so readability. Okay, so it can actually read any type of actually the files where we can actually intercalate. So this is the script. Sorry, I will open it later. So it can be actually used for in terms of the readability. Second is the versatility. Again, it can be actually connected with any of these particular tools. So there's no any, again the limitation. So for can be various purposes like web development, data analysis, uh, any system administration, automations which will be using here, and so on. Then we have the cross platform. So it can actually runs on various operating systems such as Windows, uh, Mac OS or Linux and so on. So this means the code can be written once and it can be executed in multiple platforms. Uh, Rich libraries and frameworks. So again, as I said, it will provide actually the wide range of libraries and frameworks. So it can enable user to perform the various tasks efficiently. And the examples like there are actually the coding languages such as pandas, which are actually very powerful tools. Sorry, for the data science and mathematical calculations. We have the interpreter language. So basically, the Python operates in interpreter mode, allowing code to be written and executed immediately. So usually this facilitates quick, we can say the prototyping and testing of the any type of code which were written in that particular script. Community and supports. Again, it is actually an active community with the abundant online resources and help. So even though actually we are writing this particular code, but again, so in our session, I'm actually instead of opening the Python, I can actually write this particular Python code even in the web as well. Okay, so there is actually the web-based mode where we can write this particular code and we can solve our problem. Object-oriented programming. So it also supports the object-oriented programming, generally it's called as a OOP, which means it's allowing the code to be structured and modularized using the classes and the objects. Dynamic typing. So it does not require like declaration of the variable data types. So determining the variable types and runtime, and it also provides the flexibility in programming. Just like we are actually providing some JSON format. So from that particular JSON format, you can simply copy paste that one and you can generate your own script itself. So that's why actually from the beginning we are actually not emphasizing that we should learn the complete code. But yes, just a basic of that particular code is sufficient to start such type of integrations and automations. So concept of data transferring using API. So we have the MIDAS Civil NX, and then we have the importing and exporting the inputs through the JSON. So either we in terms of the import, we have actually the Rhino with the Grasshopper, so that can be actually converted to the JSON format, and then it can be imported in the MIDAS Civil NX. Or we have the Java scripts or CSV files or the Excel VBA through the JSON, we are importing it to the MIDAS Civil NX. Whereas talking about the export, we have again the JSON converted to the Excel format where let's say the Civil NX results can be extracted to the Excel, as well as we can convert or we can passing it to the CSV and text files as well. So which means so these particular integrations, okay, along with so actually the MIDAS will actually can import all these particular software data scripts by converting even through this particular software by use of different languages, and also the same mechanism like we have actually the JSON format here, so it is possible to convert to this other languages as well. So this is just one of the example which usually you can find in our actually the official platform as well. So mainly, so one of the example here is we always actually showcasing this particular example because this is actually the need of the user. I need to actually optimize that particular session without making some iterations. So yes, that can be actually done by various ways, which we have talked about the VBA. We are talking now about the Python or even through the Grasshopper as well. Okay. So here, when you are creating already this particular concrete section, and now, so usually for the proficient way of working, we can make a code and it can be utilized to build the design processes using this particular API features. So here we are actually demonstrating how this particular Python can be used to optimize the size of this particular concrete section. Keeping actually this particular width as a constraint, we are trying to iterate the number of number of parts, and for a particular, let's say the limiting value of this trace, what will be my optimized depth? Okay, because one can be a variable, One can be a constant, others can be variable. So here when we are talking about this particular beam, okay, so it's a simply supported beam with there is actually a constant width, but we are keeping the depth starting with 50 mm and giving the limiting stress of tensile stress as 1.5 MPa. So what will be my final depth? So for that we have specified set up the actually the Python library mentioning, okay, like here mentioning, we are specifying the, okay, there are total actually the 10 elements, and through that particular 10 elements we are keeping this particular limiting stress value, okay, and for arriving for this particular limiting stress, the final depth should be calculated in millimeter. That need to be actually printed in our uh, command message. Okay, so it will go on iterating this particular depth. So here we have mentioned that, okay, so depth will be increased by 50 mm until where it is reaching this particular stress limit, that is 1.5 MPa. So that's how this particular code has been mentioned. And when we run this particular code, so it is running the analysis, and for the every iteration, so for each 50 mm of depth or 100 mm of depth, it is giving a particular depth there. So now for the setting 175 depth, the stress is 150. For next 300 mm depth, it is 12.2 mm. Okay. For next 425 mm, it is giving the stress of 4.175, sorry, 4.17 MPa. For 550 mm, so it is stopped here, and for the 550 mm, the current stress value got arrived to 1.24 MPa, which is actually the less than 1.5 MPa. So that's how the iteration will get stopped, and even you can give more iterations as well. Okay, so based on that, it will iterate, okay, how many further it will do that particular iterations. So this is actually the example, one of the example how this particular, sorry, the codes will run. So this is actually the general flow chart. So first step, we are actually importing the libraries. Okay. Now, as we have discussed earlier, we have actually the JSON library, and from that particular JSON library, we are actually maybe like we can create first the model, and from that particular model, okay, one scope we can fix the optimization. For fixing that particular optimization, what code need to be written? Okay, so for there, we are fixing the stress value, and we are keeping the variable as depth. Okay, keeping again the width as a constant as well. So likewise, for that, what procedure need to be adopted? So for that is why the library will be set. We'll connect the CivLNX to the Python code through the MIDAS API key and the base URL. Then third step will be, we will define the get stress function to get the stress results. So we'll see the results of the stress, and then we'll define the update section function. So every time whenever it is changing that particular section, okay, let's say by every 50 mm in depth or every 150 mm of depth, what will be the corresponding stress that actually it is getting printed. Okay, so it is updating that particular section size, and then we'll do the analysis. So that is a do analysis function, that is we are performing the analysis. So it will keep on checking this particular stress, and if that particular stress is within the limit, yes, so it will provide the final size to that particular beam. If not, then it will keep on iterating that particular depth, and it will give the stresses. So that is how that particular function will work. So that way we can create our own flowchart for the required output, and based on that we can give the multiple iterations. So let's see that particular example in detail, like how we can actually create this particular uh, Python code. So we are taking the example of beam optimization. So optimization of the single span beam, limiting the bottom stress, that is actually the criteria. And for meeting that particular criteria, we are increasing the depth for each analysis using the CivLNX, and the Python will help to optimize that stress. So the limiting bottom stress is 1.5 MPa, which is the user input, and the depth increment is 50 mm. Again, this is again the user input. So beam length is 5 meter with the UDL applied as 10 kilonewton per meter. Okay. So for setting up, first we will install the Python, or you can, nowadays we are having the uh, okay, the desktop based like application as well. So you don't need to, sorry, it's a web based. You don't need to install the Python as well. Then set up the code editor and such as the Visual Basic Code. Install the request module in the Python. Connect the Grasshopper to the MIDAS Civil NX using the Python API interface. Import the geometry data and loading with a single click and generate the parametric and customizable mode. Okay. So that's about this our the example. Let me actually take you the definition now. Okay. So here I'm using the Colab Google, okay, for generating this particular Python coding. You may actually install the Python as well. Okay. So let me just save as this particular file. I just open the file and we'll save this particular file in the MIDAS Civil NX, giving the name as Python example. Okay. So now, so keeping the units in kilonewton meter, go to the applications and API setting. So we have the base URL and MIDAS API key. Now we will go to the okay. So the Google Collaboratory, and here we'll click on the new worksheet. Make sure that we are already logged in. Okay, yeah. So here we have this particular Python okay interface. So you can see here. So for multiple actually the Python code to be defined, we can have this particular insert button where we can specify that one. So we'll start our generating this our Python code from here, and to run that particular specific Python code, we have the run option, perform option here. So I already have this particular Python code, so I'm just mentioning that one by one, and then we'll discuss in detail. So I'm just copy pasting that one first, and then I will explain from here, okay, how this particular code has been written for generating this particular beam. So starting with first option, which we can see here, that is creating this particular sorry. So creating this particular import request. Okay. So this import request is nothing but we are actually specifying that the JSON file, which is actually already have the standardization for the MIDAS Civil NX, that we are actually importing. So that's why in Python we need to specify this particular JSON request and the JSON uh, import JSON command. Okay. So it is used to make the HTTP request to the API and plus for encoding and decoding the JSON format. That is why we are mentioning this particular library. Next is the URL. So this URL need to be actually specified by the program. So I just copy this. Whenever you open the MIDAS Civil Linux, make sure that we are connecting to our server. So it is not, it's now connected, and copy this particular base URL here. Okay, so most of the time we need to paste that one, and then the MIDAS API key to connect the model. Right. Then we have the okay. Then we have the headers. So this is headers is nothing but whatever actually the application JSON we have specified or the MIDAS API key we have mentioned that need to be authenticated with the Python. So that's why this header is required for that purpose. Next is now from here the Python gets Python code is gets started. Okay. So first is the definition. So we are specifying the function that is a get stress. Okay. So we are assuming that there is already actually the beam, and for that particular beam, we are mentioning that particular library. Okay, I think just a moment. Okay. Sorry for this. So basically, actually, we already have the model here, and which has actually the section size of, let's say, 50 mm. Okay. So this is the actually the initial depth, and then we are actually going to iterate till it reaching this particular. So I need to actually connect the already created model, not the actually the new model. Yeah. So here we are not actually started generating the new beam. Instead of that, we are actually making this particular function for the optimization of the section. So that's why we have the get stress. You can give any name here. So this is just a definition of the function, and then this is actually the beam ID. Okay. So this function sends a post request to retrieve the stress data for the specific beam. So we are mentioning that okay, the midpoint of that particular beam and to get the stress from that. So that we are mentioning here. R is the request post URL, and from the table. So we are mentioning the first the argument. Okay. So R is basically the holds the API response, and as we discussed like during the VBA, it actually takes some data in terms of the strings. Okay. Then there is actually the argument. So what is the argument? It's a table name. There is a S. So we're specifying the stresses from the beam stress option. Okay, and then the node element. So we are mentioning the specific element number for which we want to do this particular iteration. Then keys is 6. Okay, so we can specify the element number. Let's say the 10 elements are there, the middle element is 6, and then we have the load case name. So in our model we already applied the UDL of sorry, the load case name named as UDL. So that is a UDL which is the static load case, and the component which we are looking for, that is CB4, that is the bottom stress. Okay, and the at the fourth location, that's actually the CB4. Then so this is actually the text data for that. So that is actually again the load part. In that, so the JSON command will be performed, and it will check okay, this data need to be actually retrieved for this particular stress component. And return is a float. Floating means okay, it will actually iterate the stresses for the n number of iterations. Then definition for the next function, that is updating the section size. Okay, so this is nothing but we are again specifying here okay, what is the section parameter we are going to change. So that's nothing but we are mentioning the section type as from the DB user. So this is actually the section database. That is actually the first part. If you check the our library, so the section which we have defined, that is from the DB user tab. Okay, this is from the DB user. Then we have the section name as a beam. Section before. Okay, so section before means it's basically actually like okay, what are the properties we are mentioning. Okay, so that's actually the section before. Then we have the shear deformation. Okay, use the shear deformation true. So we are giving the boolean operation whether you are considering this particular shear deformation for this particular section property definition or not, that we can specify here. Then we have the shape is solid rectangle, that is a section B SB. Data type is 2 because so first is for the DB, second is for the user. Okay, uh, so this actually the section database and all that actually can be checked from our JSON library. So you can see from the section properties, if you check here, so this is actually the database, and for the rectangular section user defined, so we have this particular direct command. You no need to type any script corresponding to that. Okay, So that is how this particular whole code is already ready. Just we need to copy paste that particular in this particular script. Okay. Then the section ith, okay, that is the ith end we are mentioning, and the size is okay. We are iterating the height, that is actually the specified parameter. So there we are closing all the argument. Then define run analysis. Now it will perform the analysis, and from that analysis, okay, we are going to check. Uh, First, it will actually post what will be the stress which is coming at the bottom of the beam. Further, we are actually giving this particular command for the optimization. So we are limiting the stress. Okay, for limiting the stress, we are specifying, okay, it is a 1.5, limit is 1.5 MPa, depth is 50 mm, which is the initial depth, and for the ith node, okay, it will start with 50 mm and it will run the analysis. So it will perform the analysis in the civil NX. There is a run analysis command, and the stress, we will get the stress at the element number 6 at the ith end. Okay, so it will print that particular stress in the output. Now further, if the stress is less than the limiting stress, so check if it is a less than limiting stress, so that is considered as a final depth. So it will show here in the output that okay, this is actually my final depth, which is in mm. Break if it is there. If not, or else it will start iteration. So considering the increasing the depth by 50 mm, and it will check for the new depth, which will update, and it will compare with the limiting stress. So we have created this particular iteration for the bottom part only. But what if there is a code for, what if we can actually specify it for the upper part as well. Upper part means let's say some actually interested for the compression stress as well. For bottom, let's say I actually iterated for 1.5 MPa, but let's say for the top I am having getting the stress of let's say 15 MPa, but the limiting value is 10 MPa only. So yes, the same code can be actually mentioned, uh, just only changing this particular get stress, and we can add the limiting stress value. Okay, we can specify here for that particular element number only, and we can give the command here for specifying to that particular element number of 6th only, because the same location it will be there. So can specify that particular depth, what will be the optimizer stress to reduce the tensile as well as compression stress at the both the faces. So that's how we can do the beam optimization for the this particular command. So now I'll just click on the run. So it will start iterating that particular code, and the current stress is 150 MPa for the new depth of 100 mm. The next current step is 13.75 mm for the 150 mm. Next is 16.7 mm for the depth of 200 mm. 9.38 mm for the depth of 250 mm. 6 MPa for the 300 mm. 4.17 mm for the 350 mm. 3.06 mm MPa for the 400 mm. So it is executing. 2.34 for 450 mm. 1.85 MPa for 500 mm. And 1.5 mm for 550 mm. So it will give the actual correct value for that same, because actually it is iterating, and the final stress got arrived at as 1.24 mm for the final depth of 550 mm. So that's how we can get this particular stress of 1.24. And if you check in the MIDAS civil NX, So let's see if I go to the results and the stress, beam stress diagram, UDL, and if you check for the fourth location, the combined stress with the values apply. We can increase these particular values to, let's say, the 3 decimal, so 1.24 mm. For the updated depth, so initially we said to 50 mm, now it got changed to 550 mm. So that's how this such type of the Python integration can be utilized for optimizing the section. Now there are various other options also there, and in fact the application areas are wide in range, because we can do the generation of the load combination as per the code. We can create some our own database for the section properties or material properties, or you can add some interface along with this particular CVLNX. So that way the different ways are there to utilize this particular Python integration with the MIDAS CVLNX. So I hope this one of the parametric modeling is clear to everyone. Now moving on. Okay. So moving on to the Grasshopper. So Grasshopper can be connected directly to the MIDAS software using the simple Python API interface. Okay. So Grasshopper is basically a parametric based modeling software. It has actually the graphical interface with the rhinos, and we can generate any type of complex geometries, and by which now it can actually integrate with the MIDAS CVLNX as well. So engineers familiar with the Grasshopper can connect it with the MIDAS software and generate the models, apply the loads, and analyze the model as well. Since the geometry is created through the Grasshopper, it is parametric and highly customizable. So let us see how through the Grasshopper and linking with the CVLNX by a JSON format will be make these particular modeling as well as the optimization easily. So the key features and characteristics of the Grasshopper, we can have the automatic node and element creation, automatic number and attributes, and the value generation, automatic API or the body completion, and the integration of calculation and data management functions. Basically, actually, these are the major functions where the Grasshopper makes useful. So exactly means automatic node and element generation means actually let's say suppose we have already created some structure into the MIDAS CVLNX, and if you want to actually customize that one, suppose it is a straight alignment and if I want to convert that into the curve, yes, that can be actually done easily by using this particular integrity. Second is automatic the number and the attribute value generation. So that is nothing but okay, let's say if you want to actually manually enter some data, or when you are actually copy pasting this particular data, so you don't need to copy paste manually, because there is actually maybe possibility of error in pasting that particular data, that may be some missing of that particular data. So that can be actually reduced by using this particular integration. Third is the API body completion. So by componenting the various functions of the MIDAS CVLNX into the Grasshopper, so the parametric modeling will be easy. So it's basically like what are the functions which are available in CVLNX that can be actually directly taken into the Grasshopper, and each and every functions in terms of geometry, in terms of boundary, loading, everything, and even the perform analysis and all, that can be done within a Grasshopper itself. Integration of calculation and data management functions. So functions which are not supported by CVLNX, such as calculation and data organization, so it can be easily implemented by using the Grasshopper. So the users can adjust the parameter values and organization the data without needing the separate calculation program by leveraging the Grasshopper's features. So there are many features available. I just show you in the software. Okay. Now about the MIDAS GH. So MIDAS GH is a third-party application that connects the functionalities of the Grasshopper a parametric modeling of software with the Civil Linux and a civil structure analysis software optimizing and enhancing the efficiency of both. So this application leverages the API technology of MIDAS Civil Linux to facilitate seamless data transfer and integration between the Grasshopper and the MIDAS Civil Linux. So this is actually the application which need to be introduced in the Grasshopper to connect with the MIDAS Civil Linux with the Grasshopper. Okay, just a short example here. I am first explaining how this particular integration works. So first, let's say we have actually some sections already defined, and then we'll connect the Grasshopper with the API setting by entering the MIDAS API key and base URL. There is a geometry which is already either created, or we can create the geometry by using the Rhino interface. For example, there's example of this particular arch bridge, and where we can just create the nodes and elements by entering the required data into this particular Grasshopper panels. So the geometry has been created. We are now specifying the static load case, and we are applying now the UDL for that particular day. So this load has been applied. Now I want to change the configuration of this particular structure. So in terms of geometry, yes, the load can be customized based on the changes we have made in the geometry. So now if you see, the alignment has been changed by simply by customizing this particular geometry into the Rhino itself. Okay, and just by entering the run command in the Grasshopper, we can able to find the further change in the Civil Linux model itself. Further, again, we are keep on changing this particular structure. Now we can see when you are updating this particular node, so based on that, your whole structure is getting updated very quickly. So that is actually the we can say the scope of why the integration is very important in terms of such type of parametric based modeling. Okay, so let us take again the same example, how we can actually create any type of such type of beam using the Grasshopper interface. So the engineers, they can actually create any type of structure here. Okay, there's no any limitation here. So let's see how this particular function will work. Let me just minimize this. I just open the new project into the MIDAS Civil Linux now. So this is now how actually we can specify the material, how we can create any section, how we can create the members, everything. We'll save this file. Okay. Yeah. Now we are let's say to start with, first we'll be having actually the MIDAS linking. So the MIDAS request can be sent from this particular terminology. Either by giving the address or by a MIDAS setting as well. Okay, so let's say here, so we have the base URL. Suppose just I'm showing you the demonstration for the simpler one. We'll go to the application, we'll connect the okay, it's already connected. First the base URL that will specify here, and then the MIDAS API key. Okay, now it got connected. Next, suppose I want to actually create some material. So from MIDAS, maybe we can actually start with, let's say, the material. Okay, so I can specify, let's say, some concrete material. So we may have the library as well. So now that actually the when you are using the latest version, so you will find all the types of material library and all. So for example, I'll take this particular case material, and suppose the grade of concrete is this one. I'll I'll give some material here. Let's say, so every time I need to actually, I'll create the, give an image, concrete. Okay. So this concrete material, I will link with this particular run, and then I will run the code. Okay. Now, once you actually specify this one, so we can find in the work tree that our concrete material with that particular material specified has been generated. Similar way, let's say I need to actually create some section. So I'll go to this section, okay, time dependent and all. So there are again the properties available. So even from the drop down list we can actually get. Let's say there is a shape user. In shape user, we can select the different shapes. Let's say I'll take this rectangular section, solid rectangle, and here I will generate the panel. I'll give the let's say the first parameter, which is 1 meter. I'll link with this one. Another panel for the 1 meter. Okay. I will link with this one. Okay. Now, if you want to actually create the beam, so here there's again option for generating the beam. So for generating the beam, we required actually the element ID. So I specify. So every time we can actually create this particular panel, and that can be actually generated with this particular element ID. Let's say the node ID. Okay. So first node material. So we can select, and you can link the material with this section. We can link with this the line element, and then just generate the line. So this is based on actually how we are actually linking this particular each and every parameter. Okay. So for a time being, I just directly open the created member. Just yeah. Okay. So this is just an example of a cantilever beam. Okay. So just I will freshly I will connect this. Okay. First I will connect the API key for this. Undo it, and we'll connect to the API. Copy and close. Then, so here we have mentioned first about, let's say there is a line element which is connected. Sorry. So first node which is at the origin, so it doesn't require any actually the coordinate for that. Whereas for the second, we are specifying a coordinate system here. Let's say x is equal to 10. Then by these two nodes, I'm going to create one line element. Okay, which is actually the this is actually we can say the creating the line between the 2 points. This line has a specific configuration, which is actually the line commands. When I click on run, and if you check the MIDAS civil, okay, so the line element has been created here. It doesn't have any material and section. Then, so this parameter one can actually easily done this. Next is regarding the material and section. Here we are specifying, let's say there is a American standard or any other standard, so that we are mentioning, let's say the American standard with grade of, let's say, C2500, okay, that we have mentioned. And here we are specifying the rectangular section which has actually the both H and B are same. So you no need to actually create the separate panels for that. So that's why both the parameters are 1 meter only, and so this will get linked with to run that particular section, as well as it will also link with this particular line element as well, which is we are already specified. Okay, that is what actually it is linked with this one. So when I click on let's say the first part, let's say I'll specify the section property, material property. So that is actually keep on updating. So here is the material property, and for the section property we can click on the section. Okay, so there is a rectangular section with 1 meter by 1 meter. Now here already actually the beam is created, the material and sections are also assigned. Okay, and now the support condition. Okay, here regarding the supports, we are actually linking this one with constraint all to that particular node number 1 only. Okay, so that's why when I click on this particular run, okay, so this will constrain the node at this particular location. Okay, so here the node number 1 has been supported with this particular constraint. Then here now coming to this loads part. Okay, so with this particular load we have again the specify like the nodal load, which is at the, again the node number sorry at the sorry, first we are actually specifying the load static load case. The name is given as a nodal, that is a static load case, and the type is the all the load types has been actually mentioned here. Just click on run. Now that will actually create the static load cases, and then in that particular static using that particular static load case at node number 6 we are assigning the load of minus 10 kilonewton in the vertical direction, the concentrated load. So when I run this command, okay, so here that nodal load will be assigned at this particular location. Just a moment. Thirty. Okay, I think that node number was assigned incorrectly. Fine. So that's about that particular load. Now when I'm going to perform the analysis, so this has not been created. Okay, so likewise actually we can create. So there is actually a question regarding the how to give the more than one material in GS. uh, we can have this direct option here, like as we actually have this particular complete MIDAS interface. So from the material we can actually again go to the every time this additional material option, or we can simply actually create the this material tab, and whenever actually we are specifying, let's say the I'll create another panel giving the name as, let's say material 2. Okay, and this for material 2 I will connect with this particular name, and let's say from the case RC I just consider, let's say C5000, and then I will run it. So that will get added in the Grasshopper. So we can actually define the n number of material, and then similar to that, then just divide this beam, and then you can assign uh, in the Grasshopper itself. Okay. So using the Grasshopper, we have actually n number of parameters that can be actually considered. So one of them actually we have tried to actually explain here. So in that, again, if you go back to the Grasshopper again, so this is actually the complete interface. As you can see, there are the different tools, okay, for deleting any components. You can actually use directly the delete command from the keyboard itself. But yes, that can be actually done. Suppose this newly material, I can delete this one directly by the keyboard as well. Here there are the different tools to get the property or get the MIDAS nodes and all. So let's say if instead of actually geometry modding into this particular Grasshopper, I can create first the geometry in the MIDAS Civil NX, and then I can call it from this particular calling it from the MIDAS gate option. Okay, there is node elements and so on. Then this is for the different groupings. This is for generating the nodes, elements, and for other types of element type like plates and solids. This is for the definition of the material, or even we can define all the properties here itself. This is for again the additional options. Additional option means you can actually create your own options as well, like the offsets and all so on. So any option like warping effect and all, so as I said, that can be done from here. These are the different boundary conditions, like different support conditions such as springs, links, the rigid links, and so on. This is for the loads. So first is the first load cases, and then the different types of loads can be assigned by using this particular different functions available. This is for the temperature loadings and the pre-stressing along with the pre-tension loads as well. Uh, okay, this is for the load case. So first we need to actually define the load code. For example, I'll select here the code, and let's say the India. Okay, I think I have not actually set it. Let's say the Astra LRD. Okay, and then I'll run it. So the load code will be get set, and then further we'll define the static load cases. So before that we need to specify the lanes, right? So there's a traffic line lane and surface lanes. So I can actually start with the traffic line lanes as well. So here how many number of lanes are there? What is the different factors, multiple presence factors and all that can be mentioned from here. These are the construction stage definition that can be again built by already created the groups and then can be linked in the different construction stages. Here we have the different analysis types as well, like a buckling, eigenvalue analysis, p delta analysis, and so on. And we'll see the results. So there is a direct command for performing the analysis as well. So here we can connect this particular perform analysis option by just performing the model which you have created with that one. So we can use this particular load case and whatever the geometry we have created. Okay, and then we can do the performing analysis. Okay. Right. So I think so you may actually find the various options available on our support site. Let me actually take you to our again the site. So it's like so kindly register on our website to get more about this particular details. Sorry. Okay. So here in this particular support option, we have actually the support and the academy available to know about these particular features and all. And in terms of the resources, so we have the different blocks and all. In the products, the civil Linux, you will find the major applications, how this particular all the features and all will be used. And for the MIDAS API manual, and yeah, regarding the various examples for the grasshoppers and for Python, so we recommend to go to our support.midastudio.com, and under this for the resources we have the API manual, In this particular API manual, you will find the examples related to the Python as well as the JSON. So let's say for the Grasshopper as well. And the corresponding, we can see the manual, like for creating the elements and all. So the already actually the library has been created here. So the user can directly use that particular library for generating the structures. And some examples, ready examples are also given. Okay, for Python it is given. So you can actually use directly for the practice purpose. Yeah. Here, if you check at the bottom, we have already actually some Python files are there. So that actually you can try generating as. So first is for the simple beam, second is for the alignment creator. Like if there is a straight and we need to convert that into the code. So such type of alignment can be readily created. There is a division of the elements. If there is a single line element which you have created, we can divide that into the number of parts. So that has been mentioned here. And also the spline tangent. So how to again create that particular alignment. So that has been actually explained here. Yeah, so that's from my side, and I hope the sessions are helpful. So our next session will be based on the FENX. So using the FENX, how we can actually use the detailed analysis and the detailed modeling of a particular component. So maybe we'll just take the simple example of the anchorage and how the cable anchorage can be modeled and can be analyzed as using the solid elements in the MIDAS FENX. So let's see you in the next session, and yeah, thank you for attending the today's session. So we'll share you the recording of all the sessions together once the next session is completed. So thank you and have a nice day.